March 2026. The Strait of Hormuz is closed. As a massive commercial drone swarm takes flight, global oil prices surge past $120 a barrel. Out in the Gulf, the USS Abraham Lincoln's Aegis radar system suddenly registers 47 simultaneous targets. It is a saturation attack. Cheap, expendable drones and low-flying cruise missiles converge on the carrier group all at once, aiming to overwhelm its multi-billion-dollar defense network through sheer volume. Below the surface, the threat is equally severe. Unmarked Iranian midget submarines lie in wait in the shallow, muddy waters. To counter them, the U.S. Navy deploys Virginia-class attack submarines, massive, silent hunters that track mechanical pulses through the seabed to neutralize diesel-electric targets before a single torpedo can be fired. But a month into Operation Epic Fury, the limits of pure firepower are becoming obvious. 30 days of Tomahawk and bunker-buster strikes had leveled inland missile factories and crippled coastal radar networks. Yet the 21-mile chokehold remains entirely impassable, heavily populated by thousands of passive, hidden naval mines waiting on the seabed. A cruise missile can obliterate a radar dish or collapse a mountain tunnel. It cannot sweep a minefield, nor can it hold the islands overlooking the shipping lanes. To clear the water, someone actually has to hold the ground above it. To break the deadlock, the U.S. military stops trying to push through the mined waters. Instead of a traditional amphibious landing, they bypass the sea entirely and launch a massive assault from the sky. The operation begins with absolute electronic dominance. E-2D advanced Hawkeyes coordinate the theater, feeding data to EA-18G growlers that blast artificial noise across enemy frequencies. This creates a total information vacuum, blinding the surviving coastal defense networks. Inside that electronic silence, the 31st Marine Expeditionary Unit moves in. Their primary transport is the MV-22 Osprey, a tilt-rotor aircraft that lifts off a flight deck vertically like a helicopter, but rotates its engines forward to fly at the speed of a fixed-wing plane. Looking at this diagram, we can see the geometric advantage. The most common shoulder-fired surface-to-air missiles in the Iranian arsenal have an effective ceiling of roughly 11,500 feet. The Osprey transits at 15,000 feet, flying safely above the threat envelope for almost its entire journey. The only true vulnerability is the descent. But because the Osprey cruises at 270 knots, nearly double the speed of legacy transport helicopters, the reaction window for the defenders shrinks drastically. From the moment they detect the incoming drop to the second Marines hit the dirt, the garrison has less than 4 minutes to respond. By moving the assault into the high-altitude transit lanes, the U.S. military renders 40 years of static coastal defense architecture mathematically irrelevant. The primary target of this aerial envelopment is Karg Island. It is a barren 12-square-mile rock in the Persian Gulf, yet it serves as the processing bottleneck for 90%. The Marines don't need to sweep every inch of the island. Karg has no natural fresh water. It relies entirely on massive desalination plants to keep its operators alive. The Marines concentrate their armor and seize those specific facilities within the first hour. By capturing the water supply, the attacking force places the local garrison in an unwinnable position. The defenders must either surrender or die of thirst, allowing the U.S. to capture the region's most critical economic valve without fighting an extended war of attrition. Seizing a rocky outcropping takes 24 hours. Holding it requires a constant, heavy flow of ammunition, fuel, and medical supplies that the initial assault force cannot carry. By day 10, these secured islands face acute shortages while surrounded by live minefields. This requires a highly specialized sustainment fleet. Enter vessels like the USS Comstock, a dock-landing ship built with an interior well deck the size of a football field, designed to carry heavy transport vehicles right to the edge of the contested zone. The heavy lifting is done by the LCAC, a massive hovercraft capable of hauling 60 tons of cargo, including M1 Abrams tanks and fuel bladders, directly from the ship to the beach. Riding on a pressurized air cushion, the LCAC spreads its weight over a massive area. Physical water pressure drops, so seabed naval mines fail to detonate. Operating at an industrial tempo, they cycle continuously between fleet and shore, delivering fuel and evacuating the wounded. Without this continuous logistical umbilical cord, the Marines would be isolated in a matter of days. Firepower captures the ground, but it takes raw industrial engineering to hold it. That engineering comes at a steep price. Out at sea, the U.S. Navy's most advanced supercarrier, the USS Gerald R. Ford. Ford is beginning to buckle under the strain of a 283-day unbroken deployment across 3 theaters without a single maintenance reset. The Ford's electromagnetic launch system and advanced arresting gear depend on a network of interdependent software and power loops that have never been tested at this duration. When a fire breaks out in the aft laundry, it isn't the localized damage that pulls the ship from the line. It's the reality that the ship's complex digital systems are already operating at their absolute limit. There is no backup left for a crew and a grid worn down from the inside for 9 months. To cover the gap, the Navy must sail the USS George H.W. Bush, the final Nimitz-class carrier ever built, relying on analog steam catapults. The Navy trades the high operational ceiling of the Ford's digital launch systems for the reliable floor of the Bush. The older mechanical systems break in predictable, fixable ways, offering a baseline of endurance that highly sensitive digital networks struggle to sustain over prolonged, continuous combat. Winning the Strait of Hormuz is a feat of endurance. The outcome is sustained by an agonizing, fragile chain of logistics, hovercrafts, and sheer mechanical persistence.